Morning, everybody. Thank you, Rachel. It's been my honor to be involved with joint venture and also to be here with you guys to introduce properly JB. As one of the co-founders and the chief technology officer at Tesla, JB today is responsible for all the software, electronic and propulsion across Tesla's portfolio and direct operational responsibility for roughly a quarter of the company. This includes all aspects of powertrain R&D, engineering, and production. JB is also the point executive for driving O&M partnership relationships with Toyota, Daimler, Panasonic, as well as others. In addition, JB's managing the creation and construction of Tesla's Supercharged network, which just opened up. Congratulations, opened up a couple weeks ago. It's 100th station. So congratulations. Just a little bit on JB that I found interesting in preparing for his introduction that I wanted to share with you. His passions for electric vehicles really began at an early age, starting with rebuilding of electric golf carts, which is definitely an interesting spin, an early predecessor of Tesla, if you think about it. At the early age of 14, converting a Porsche 944, which held a world electric record for racing, which is pretty incredible. He continues to push the boundaries for electric vehicles advancements and enjoys exploring new innovations from renewable energy systems as well as energy storage solutions. Prior to Tesla, JB was the chief technology officer and co-founder of the aerospace firm Volcom, which designed and specialized high-altitude electric aircraft platforms, which, think about it, the Airbus E-Fan, as well as the Solar Impulse, which landed nearby here last year, are great examples of some of that early work. JB holds a Bachelor of Science in Energy Systems Engineering and a Master's of Science in Energy Engineering from Stanford. He's the holder of 10 U.S. patents and is on 19 pending patents for applications of motors, batteries, powertrain components as well. In addition to his work at Tesla, JB serves as on the board of directors at Solar City, a company that knows a little bit about customer-side distributed generation as well. So please join me in welcoming JB to keynote the symposium.
Thanks, Jeff, for the kind introduction, and thank you guys for inviting me. It's cool to be here and fun to talk about storage. I really love batteries. I think I might love batteries more than cars, so this is kind of a passion of mine. And, well, maybe we can jump right in here. I think a lot of you probably already know the high level about Tesla, so I don't want to drag us through too much detail on Tesla, but I thought I would give you a quick summary and history of sort of why it makes sense that we're involved as deeply as we are in the energy storage market, and why that growth has expanded into stationary energy storage. So kind of going back to the very beginning of the sort of EV movement and what this whole landscape looked like earlier in the century, battery technology just had not improved very quickly. And it was kind of amazing that even in the 90s we were building electric vehicles with lead-acid batteries. That was the state of the art when Tesla was founded in many ways. There were a few nickel metal hydride vehicles out there, but by and large, lead acid was kind of the defining technology. And lithium ion is what completely changed the game here. There were these massive improvements in volumetric energy density, the amount of range we could get per mass of battery and per volume of battery in the car. And it suddenly went from a really, really niche market to something that could suddenly compete both in price and performance with gasoline vehicles in the right market. So that was really the big catalyzing event in many ways. In my mind, technologically, that launched the resurgence of EVs and launched Tesla. And this is about what lithium-ion R&D looked like at Tesla in 2003. So it's also pretty amazing how fast this market has changed. There were no companies doing lithium-ion battery development for cars. Tesla was the first one to actually commercialize and sell the lithium-ion car to consumers. And today that's sort of commonplace. Almost every automaker has a lithium-ion either hybrid or plug-in hybrid or full EV somewhere in their roadmap. And also lithium-ion has become a dominant factor in stationary storage. So it's amazing that in the span of about 10 years, how much improvement, how much change has happened in the market. And we took that first sort of lithium-ion R&D and applied it to, at the time, it was a pretty new concept, which was making an electric vehicle that would push the boundaries on how far it could go, how fast it could go, that wouldn't try and just be an economy car, but would be something that absolutely challenged internal combustion on its kind of home turf, with the sports car. So this was the Roadster. This was the first car that we introduced and sold back in about 2008. It sold about 2,500 cars worldwide, which was great. It sort of exceeded many of our early expectations of success, but it's still a tiny market when you look at the overall car market. And at the time also, this was the biggest battery pack anybody had ever imagined putting into a car, let alone using lithium-ion for. I remember tons of discussions where people were just terrified of the concept of a 50 plus kilowatt hour lithium-ion battery pack going into a sports car. That just, they would run for the exits. And today this seems kind of like old technology. It's sort of amazing looking at the energy density metrics on this pack, and in the cost metrics of how much it's improved. But this is where we got started. And also a lot of our early optimism for the entire electric vehicle space hinged around the rate of improvement that we were seeing in those days with energy storage. And this is sort of an old chart that I sort of intentionally didn't want to update past about where we introduced the Roadster. But you can really clearly see what happened between the sort of last generation of electric cars. Perhaps the EV1 is kind of the best example of that. And when we launched a new generation of electric vehicles that were focused around lithium-ion. And you had about a 2 times increase in overall energy storage capability of the pack in the car. So it went from something that was around 300 watt-hours per liter to around 600. And that clearly translated straight into a doubling in range. It was also a mass reduction and a cost reduction. And we looked at this graph, and we spent a lot of time talking to all the different companies that were driving the improvements here. And there was nothing, and still is today, nothing that's clearly starting to plateau on this graph. These improvements are still compounding and improving. And it's not a Moore's law, it's not close to that, but it's something close to a doubling in performance of energy density performance about every 10 years, which seems kind of pedestrian, sort of slow moving, until you really think about what that means, and how big and heavy and revolutionary these battery pack is. A doubling of energy density in a battery pack from where we were in Roadster to where we would be 10 years from then, is pretty phenomenal. And that's close to the level of performance and improvement we've been seeing. Model S, was designed and introduced about 5 or 6 years after, maybe about 5 years after the Roadster, and we saw improvements of around 40% on the battery technology, the fundamental, chemistry, the packaging of the battery pack itself. And that directly translated into how we can get close to 300 miles range in a Model S, almost 85 kilowatt hours of energy storage in a pack that's actually smaller than the Roadster pack. And again, these improvements are not standing still. We're continuing to watch the same doubling every 10 years out for at least another 10 to 20 years. And it's incredibly exciting on the car side because it doesn't take many more, even tens of % improvement before the competition with internal combustion cars just spreads everywhere. And it's also, I think, interesting what it does for the volume of this whole industry. This has been kind of our long-term product roadmap strategy of continuing to strive for higher and higher volume and lower price point. Tesla wasn't founded to go and make more sports cars or even really more cars in general. The world has a lot of cars. We were founded to try and drive a revolution in energy technology and to change the way transportation is powered, make it more sustainable. And to do that, you really need to make a dent in volume. And selling a few thousand cars here and there doesn't totally move the needle. You need to sell hundreds of thousands and millions of cars to move the needle. So our strategy has been continuing to innovate on all the core technologies that have leverage and can move the needle on this, and energy storage is the biggest one. You can't win this battle without reducing the cost and improving performance of energy storage. So this is just a quick snapshot of the different cars we're doing today. I won't dwell on this too much, but the Roadster and the Model S. The Model S is by far our focus. It's the majority of our business. We also have built battery packs for some other OEMs, Mercedes and Toyota notably, the RAV4 and a B-Class electric vehicle that Mercedes is launching basically right now. They've had some press about this already. And here's a snapshot of where the Model S pack is at. So this is kind of bringing us forward to sort of today's architecture and today's technology. And the scope and scale that we got to and are currently operating at with Model S. I can't disclose our exact price and cost figures, of course, on batteries, but it is at a cost point that we realized was eminently competitive on different markets outside of cars. And we've also been increasing our scope upstream and beyond cars as we start talking to more and more utilities and start working with charging entities, people installing charging infrastructure and negotiating rates for those different chargers. Working on the Supercharged network has really brought us much further upstream from the car, thinking more holistically about all the energy that powers it and how you get all the way from creating the energy source, whether it's solar, wind, whatever it might be, all the way back into moving the car. So it's the price and cost where we're at with the current Model S architecture, which led us to really drive a new innovation into a different business unit that would start thinking about stationary storage. And one of the key things here was realizing that energy density is a key pathway to low cost. It's certainly true in vehicles, and it's not totally intuitive, and a lot of people in the automotive market have kind of gone the other direction, which is lowering energy density in hopes that lower technology will be less cost. But we've really focused on the other side of the spectrum and looked at the highest energy density chemistry systems that we can find in the world and highest energy density cells that we can package and build into safe packs. So this brings us up over 200 watt-hours per kilogram today, pretty substantially over. And that also has great benefits in stationary storage. The footprint of real estate needed, whether it's in a building or just even on a piece of land outside the building or at a substation, wherever it might be, footprint always matters, and it has a big impact on cost. So this has been quite beneficial there too. And coming back to this slide, the other key piece here that we've recently started really focusing on heavily is the volume side of this. We've been pretty successful at hammering down the cost and gotten to a place where we're quite confident in where we can get on vehicle cost projections and on storage cost projections. That DOE graph is actually, I think, reasonably solid and maybe even conservative in the long-term time frames. But there's another secondary problem, which is the overall volume capacity to build energy storage in the world. And a theme I think that needs to get repeated is maybe this whole group is not thinking quite large enough scale. The S-chip is great. It's incredibly helpful to sort of bootstrap the market and get California started. But it's tiny. It's really, really tiny. It's just a drop in the bucket of the total market size for energy storage. So, and if we look at just our volumes needed for our Gen 3 vehicle, our target is to build around 500,000 Gen 3 vehicles per year. And that's what we can do in our Fremont factory just across the bay. That's not some revolutionary new huge car factory that's never been built before. That's just turning on the factory that's already sitting there and running it back up to its existing capacity. So from the automotive construction point of view, that's not really that revolutionary. From the energy storage point of view, it's a complete game changer. And it doesn't take too much napkin math to start to figure out what that means in terms of how many megawatt hours, gigawatt hours of energy storage you need to do that. But it's huge. And this little graph is, I think, a pretty interesting one to focus on. It's the world market, or the world production capacity for lithium-ion batteries. So if you look in 2013, it's worldwide about 32, 33 gigawatt hours of lithium-ion batteries were built. And Tesla in 2014 is projected to use about 3 or 4 gigawatt hours of energy storage capacity. That's just for cars. The stationary storage side of this is still very small. But these are getting to be pretty serious numbers, and that's on the order of 10% of world demand for lithium-ion batteries. That doesn't really keep scaling up in a really good way. So when we double and look toward 2020, when we think Gen 3 will be running at about 500,000 cars per year, that's about 10x our current volume, which is very doable from a market point of view when we look at the cost point, but it totally breaks the supply model for lithium-ion. So we've started to go and realize that we need to build new capacity to make lithium-ion cells that's equal to about today's worldwide production capacity. It sounds really scary, but again, this is very small scale compared to the overall car industry. In this 2020 case, we'd still only be supplying about 0.5% of the new car market in the world. That's not like overwhelming market share by any definition I've ever heard. So it's pretty amazing how much growth there will be in energy storage. And the associated thing that's also incredibly exciting about this is what this does to the cost point of that energy storage technology. We're not in a world where we're just growing production capacity by 10, 20, 30% and expecting maybe like 5, 10% price and cost reductions on that storage. we're in a world where we're doubling the complete worldwide capacity for energy storage in a single factory. This is a growth phase where we're reinventing kind of the whole supply chain and how we build this stuff. And there are major opportunities for how we can reduce the cost of all the components going into that. So the really cool thing is what that does for all these secondary markets and ancillary markets that are not just the simple car market. Getting to price points on the battery pack alone that start to make sense. As Janice was saying, you can build economic business cases all day long for customers that have no incentives. And I'm pretty bullish that this stuff can actually scale faster than the car market. The grid storage market, it is kind of slow to mature, but once you cross some critical price thresholds, you're really dealing almost more in commodities. Nobody really cares that much about kind of how sexy your stationary battery pack is or what the styling looks like. It's a much easier sales proposition. If it saves money for the customer, and you can clearly do that in a bankable way, it makes sense. You'll sell it. It'll scale. And today we're in a world where that happens in some cases, when you can aggregate a lot of interesting demand streams and aggregate incentive structures. So it's a bit complex, but in the not too distant future, we're going to be in a world where that business case makes sense almost everywhere, without any incentive structure. And then the scaling happens really, really fast. And the scaling goes up to levels that are much bigger than this. So just a quick snapshot of some of the things we've been focusing on here on how to reduce this cost structure. We're going far upstream in the cell manufacturing process. We're not just looking at how do we do a winding of a cathode or anode better, but we're looking at coating, we're looking at the material synthesis to build the cathode and anode. We're actually going all the way back to literally some of the places where the raw materials come from. If you start breaking down the cost and build a big pie chart of what's driving cost on a lithium-ion battery today, materials are actually a reasonable part of that. But even those material prices can be reduced if you drive the right volume and drive purchasing power into how you're buying them. So it's quite exciting. And the other piece of this that is great is we get to have pretty positive impact on how all this is done. Obviously we're doing this to drive and improve sustainability in the world, and that certainly doesn't help us if we use unsustainable practices to build battery packs for a sustainable product. You're going in circles and not really improving things as much as you might think. So it's fun to be able to use the leverage of the demand, in order to drive good behavior into the supply chain. Low emissions, good labor practices, all of this, optimizing the logistics trail for moving materials all the way from their source through the factory and from the factory to vehicle production. And this is sort of a schematic and some of the specs on the so-called Higa Factory that we're actually in the middle of getting ready to break ground on in less than a month. And the overall target goal here is cell production on the order of about 35 gigawatt hours per year and pack production of about 50 gigawatt hours per year. And again, this is just to meet the needs of what we see in the Fremont plant for Tesla only. This is not sort of a merchant plant trying to satisfy the whole world car demand. It's satisfying the demand of one reasonably large car plant. So we've intentionally sized the pack output here a little bit more than the cell output to try and focus on other markets. And stationary is the biggest one of those. So we're basically allocating about 15 gigawatt hours per year of capacity in this plant to build stationary battery packs. So when you come all the way back to sort of the California mandate for energy storage by 2020, it seems like a huge amount, and it seems really remarkable, and drives the industry faster than it could ever be driven before. But we're actually quite a lot more bullish than that. I think that mandate will get met and far exceeded well before the time frame on it expires. And this is something like 10 times more allocated capacity for packs than just the California mandate by the same time frame it's supposed to end. So I guess again, we should all be thinking bigger. The grid opportunity here is huge, and the sort of economics that are going to drive this forward are happening much faster than many people expect. So Tesla and stationary storage. Where we started? Where did we start? I should say. Well, about 2 years ago, we started adapting the same architectures we use in vehicle packs into stationary storage packs. And we didn't reinvent the wheel here entirely. We leveraged a lot of the good engineering work we had for vehicle packs and started building, at first, residential energy storage packs. And we wanted to meet the need and the sort of demand of most people that had solar installations and also owned a Tesla. And a lot of those people wanted, better energy security in their house. They wanted to be able to island their whole system, if the utility went out, which they couldn't currently do. And they also, frankly, wanted to have the ability to sort of just play with energy in their house. They wanted to be on the cutting edge of, having the ability to do some peak management in their house, even if there wasn't a big economic incentive to do that. So we started this, as I said, a few years ago. And, it has scaled somewhat, but, we've been somewhat plagued with our partner Solar City and interconnection challenges and just the ability to sort of drive this into the California rate base as fast as we thought. And today I think, I'm not sure the total numbers, but it's perhaps around 1,000 of these systems have been installed. And it really hits exactly, I think, the point of a lot of this conference, which was how do we invent a system that lets users manage their own energy bills, and do that in a way where you can try and aggregate a lot of different consumer-side financial benefits. So backup power being one of the biggest benefits that's somewhat hard to quantify, but comes in at the residential level. And then the ability to operate, especially if you have a renewables energy system, a solar system, to operate as an island. And it was a big shock, of course, after all the power outages on the East Coast, and the people that had solar systems couldn't just automatically island. Most people today still think that if they install solar on their house, they're off-grid. I would take a poll of most people, and I bet that's about a 75% assumption, even though it's totally wrong. You're absolutely on-grid, in fact, totally dependent on the grid for the solar to even operate. And that's not necessarily a bad thing. It's actually a good synergy of using the grid, but it's confusing to people. And as soon as the grid fails, they're really quite disappointed that the investment didn't somehow let them be independent. So this does that. And the other thing we started doing here, kind of as an experiment, was aggregating these systems together. And this is also somewhat experimental, and I'm not entirely sure this is the way the market will play out, but you can certainly do an imaginary system where you have numbers of different houses. They're linked together with communication, and you can dispatch all these batteries intelligently based on market signals that won't be on the customer side of the meter. So it's starting to balance customer side needs with needs of the utility or the ISO that are outside the meter. And you can kind of keep doing this. There's no obvious limit to how big this thing can get. But the challenge is, how do you sort of lump all these different economic streams together and make a business case out of it that makes sense? And it's pretty challenging. How you sort of make that value proposition to the customer and then actually get paid by either an ISO or the utility to do these services is still very much not really fully baked. It's not really done, and it's part of why you don't see companies leaping into that space and growing very quickly. As a result, we've somewhat expanded our product line and started to look at larger scale systems. We're still doing the residential systems and still installing those through Solar City as a channel partner, but we're also now putting much more focus on the larger scale systems, and we've put together kind of a single modular unit, also based on the Model S pack architecture, of about 400 kilowatt hours. And it's a 2-hour rate pack, so it's 200 kilowatts, 400 kilowatt hours, and it's sort of a single skid unit. And this is about the size of a big shipping pallet, if you want to think of it that way. It's quite dense. And each of those little file cabinet-like vertical things is one Model S pack, more or less. Rearranged entirely and stacked vertically, but it has the same cooling, the same safety, the same electronics and software, and all the things that we have validated and are building in very high volume in Fremont. And we're now in full production on that sort of skid product. Here's one that's going in actually at one of our Supercharged sites in Tejon, California. It's down on I-5. If anybody's ever done the San Francisco to LA drive, you're sitting out there in I-5 for about 4 hours, pretty bored, but this is one of the Supercharged sites that has a lot of traffic for us down just before the Grapevine, if you're heading south. And maybe to pause on that, we've started piloting these installations and the controls for them with our own needs and applications, and Supercharged is kind of the perfect application for energy storage. It's big enough that we can really justify a lot of investment in controls and the hardware to optimize a single site. And it's an incredibly peaky load. It's probably one of the worst loads. We're also paying the meter and paying the bill on this. We have Tesla funds this 100%, and it's free to customers. So we have our own demand charge, we have our own utility interconnection and everything else. So we get the benefits, of course, of doing things like this if we can install storage and control it properly. And just to kind of look at what that looks like at Tehom, this is sort of a cool graph from very recently. It was just, I think, earlier this week. But you can kind of see, if you pick apart this bottom graph here, the blue graph, the top line, is what the site would do if there was no energy storage. It's just the straight demand for electricity from the superchargers going out to the cars. And you see it spiking over 1/4 megawatt. So that must have meant there were probably around 3 or 4 cars supercharging simultaneously at different states of charge and power. But that's a pretty big peak, and it's really, really short. That's a peak that might only be like 20 minutes. So we might just be over the limit of ratcheting to a peak demand for the entire month, just when 3 or 4 cars happen to come together. It's something you'd really want to knock down. And then in this case, the red is the resulting meter import. So that's the resulting load of the site after the battery is contributed to it. And you can see the huge difference. The green is the battery support. So the battery in this case, this is about maybe about a 300 kilowatt peak battery pack. So it's knocking down the majority of this peak. And we get to a load profile that's actually reasonably continuous. Even though we have cars coming and going and charging at 100 kilowatts plus, one after the other, some of them overlapping. So this has been a really, really great proof of concept for us. And it's taken a while to work out the controls so this actually works well and happens smoothly. But it's, I think, a wonderful example of a really clear economic viability for energy storage. So we're rolling this out at almost all of the supercharged sites over time. This was the very first, and we're continuing to do more. So that's kind of the customer side of the meter. And I don't want to dwell too much on the utility side of the meter, but to say that I do think it's going to be an incredibly important part of the future of energy storage at this large scale. I think it will end up being one of the big market drivers. And Janice mentioned some of these same curves, but this was the California ISO curve for yesterday, I believe. This doesn't look so bad. It actually looks pretty darn good. We're kind of in a reasonably nice time of the year for this, so the whole load is not very peaky. But the sort of big transition that has to happen, and the duck curve, so-called, is really one of the big kind of focal points to rally around this. Is driving to more and more renewables, and I think for a number of reasons, most people would agree that over time we're going to keep seeing more renewables on the grid. The economic drive for it, if nothing else, if not renewable portfolio standards, will keep driving more solar and more wind. So in the long-term future, storage is critical on the grid at a bulk level, more so than just managing customer demand. There's a whole sequence of different value propositions for storage, but it starts with things like backup power and then moves to customer demand management, and then ultimately the real guerrilla application is how do you enable super high density, high percentage renewables on large sections of the grid. And that's the bulk market for storage that I think is the one that drives demand, just totally nonlinear in the next decade. This is the same graph that Janice showed, just maybe a different view of it. But it also, in my mind, is not really thinking big enough. Almost everyone realizes that in the very long-term future, we have to get to 100% renewable grid. That seems logical, right? It's just maybe, is it going to take 50 years, 100 years, who knows? But we have to get there. And to do that, this will look really tame. This is maybe only a 20% or 30% renewable grid. As you start adding more and more solar to get to a 50, 60, 70% renewables, you've completely warped and changed around your whole concept of when the peaks happen, and there would be negative midday demand. There would have to be, if you actually wanted to have 100% renewables. You have to over-generate clearly when you have the energy. So storage just becomes an absolute imperative to get there, and at some point, there isn't a choice. Here's kind of yet another view of that with solar overlaid. I think it really makes sense, what this graph is doing when you look at that yellow solar curve. It's sort of obvious that as we keep growing that yellow curve bigger and bigger and bigger, whether it's with distributed solar or utility scale solar, it doesn't too much matter. It's causing the same effect. The sort of necessity for storage at the grid scale is going to be really key. And something that I think also we have to keep in mind as an industry is the utility rate base and all the incentive structures for how you deploy storage are pretty wildly inconsistent right now. It's something that's immature and changing and growing so fast. But you could install a residential battery pack where the incentive is clearly to have it sit 100% charged and just do backup power demand. Or you could do a small commercial pack and install it to follow this sort of peak rate base and try and respond to the time of use signals and whatever your rate structure is. But a lot of times, the rate structure that you might see, even as a small customer, would be totally opposite from something like this. It's telling you to discharge the pack as fast as you can, at the same time when solar might be generating the maximum amount. So I think there's a really interesting, revolution in how we think of when and how you should dispatch storage as an asset class, coming to this whole industry. It's a fascinating problem, but it has to keep in mind, not only the sort of small-scale distribution bottlenecks that happen, but also the big-scale system-wide impacts that will happen, as renewables start to get to higher and higher density. And we're just not set up for this right now. The utility has a piece of it, ISOs have a piece of it. The grid, in some cases, doesn't even quite have the information it needs to manage other parts of it. And just to look at some more cool pictures. So this is one of the bigger installations we've done. We did this one last year, and this is at the Fremont factory. This is about a 2 megawatt hour battery pack. So it's 5 of those skid units that I just showed kind of one picture of. This unit's up and running. It's been doing duty managing the sort of loads at the entire Fremont plant for about the last year, which is pretty sweet. It manages maybe about 10% of our peak demand at the entire factory. And it's a big load. That is a 100 megawatt substation tied in at 100 kV. And it's a direct access customer. So it's a great pilot facility where we can start to experiment with when we want to manage that and start working with the ISO directly on this. But still, it's a relatively small pack. 2 megawatt hours doesn't seem very big when you kind of plot it on top of our overall utility bill. It's sort of like a little teeny thing. So the scale that we need to start operating at is just so much bigger than this. And seeing that graph of something like 100 megawatts, or maybe it was 200 megawatt hours total of battery installation in the world today, it's really, really small. This alone is like 1 or 2% of that. So the level of growth is very exciting. Here's just another picture of that where you can kind of see more clearly all the different modules and packs. We're in the process of doubling this right now. So it'll be about 4 megawatt hours in the next probably 3 to 4 months. And Tesla is driving as fast as we can into this space. It's something where I'm really passionate about it, and as an overall mission statement, it aligns completely with what we're trying to achieve, which is how do you make the grid more sustainable, and how do you generally drive sustainability and energy innovation into this whole space. I see us more as an energy innovation company in a lot of ways at our core than even a car company. And this is sort of one of the first big aspects of that. Supercharged is another. So here are some quick mechanical drawings on that. I don't know if people care about the details here, but this is about an 8,000 kilogram kind of unit. It's fairly dense, but also fairly small. And the footprint again is quite competitive. That's something we've that's a strength coming out of trying to design really compact battery packs for the automotive industry. And this is a product that we're putting a lot of focus in to scale all the way up to utility class solutions. So we're looking at installations that go all the way up into the hundreds of megawatt hours, doing distribution level support directly with utilities. And we're seeing that to be cost effective today. It's definitely much closer than people think in terms of the cost competitiveness of batteries. And SCHIP has been very, very helpful to sort of bootstrap this industry, and it's still critical today. I'm totally in favor of continuing it to whatever level it can, but the industry should be careful not to get too dependent on this sort of stuff. And I think we have to be careful and mindful that every installation that's being done should have a clear roadmap to what benefit it's providing, and not have that benefit totally reliant on SCHIP. So that's how this whole thing scales and doesn't end up being a sort of a small blip when the incentives have to taper away. There's also, as I mentioned, a layer of control and communication here, which is quite fascinating. There's enormous amounts of really interesting problems that have to get solved surrounding how you dispatch, control, and monitor all these different assets. I think there will be a whole fleet of different startup companies that are going to end up doing this stuff and playing key parts in this. Right now we're doing a lot of it for these projects just because we have to, and because we know the characteristics of the batteries very well, and we're building good relationships with the customer utilities or companies. but that this is a right market for more innovation and more communication with utilities, all of it. It's surprisingly difficult to figure out exactly what you do with storage. It's kind of a nice thought experiment to sort of say to a customer or a utility and say, well, if you had a hypothetical battery pack, you have a magical 1 gigawatt-hour battery pack that you can control however you wish, what would you do with it? And a lot of people kind of scratch their heads and they don't know exactly. They haven't thought through it and figured out, well, what would that mean to my generation mix, to how I dispatch generators, to the economics of utility, the electricity for the rate base. They have to think through all these questions, and now is the time to start doing it. So with that, I'll maybe wrap up and do some Q&A. I'm kind of curious to hear what you guys want to think about. And maybe just one final closing thing is, toward this quote, this is, I think, really quite accurate for this industry. It's not going to be driven with a stick. There's not something where fear over CO2 or fear over these other things, I think, will be the driving reason for change. Certainly that's important. I believe in that deeply. But I think the economics and the sort of compelling technical merits of the solutions are going to be what drives it. If you look at the price of wind generation today, it's cheaper than anything else that people can install. You can sign power purchase agreements for wind in Texas today. They're under 3 cents per kilowatt hour. Long-term PPAs, bankable, and that's incredibly cheap. But it needs storage in order to drive it to a higher percentage of the mix. Texas is already curtailing wind in some of its high generation regions. So that's kind of a clear signal that storage is really absolutely needed there to keep scaling and using that cheap wind as fast as people want. Solar is not far behind. And I think over 90% of the new generation in the United States was renewable last year. So if you kind of just keep playing that out, you're very quickly going to get to a saturation point, and you're already there in some places with expensive electricity like Hawaii. So anyway, I'm very optimistic and very excited about the market. It's going to grow faster than people think. So some questions, please. Yeah, in the back.
You showed that graph of the lithium batteries growing. Can the world support that? I mean, you pointed out that the small amount of batteries for cars. I was wondering whether that's scalable, and also related, are the lithium batteries recyclable?
Well, I think when you say can the world support that, do you mean from like the primary resource and the materials point of view? Yeah, well, if you look at what goes into lithium-ion batteries, I mean, all the different energy storage technologies should have a similar analysis, but lithium-ion batteries are primarily based on graphite and carbon, for the anode, and then largely on nickel. And it's quite nickel intensive for the chemistry we use on the cathode. Other than that, you've got steel in the can and some polymers in the separator and the electrolytes. Nothing too fancy, ethylene carbonates and things. There's plenty of raw materials, and there's a lot of hype about lithium shortages, but we've dug into that pretty deeply, and it's just not true. There is an overabundance of lithium that takes us way beyond any of these projections. And I think there's a bit of a bubble in the lithium market where people have gotten really excited because it's in the name of the battery, but in reality it's not the price driver, or I should say the cost driver in the materials breakup for the cell. So, yeah, in the back.
Hey, Craig Lewis with the Clean Coalition. I want to thank you personally for your vision and commitment to energy storage and beautiful automobiles. I am a happy Tesla Model S owner, and it is the greatest driving machine ever invented to date. I'm sure you come out with something even better.
Thank you.
My question is really aligned with what I work on every day, which is accelerating the transition to renewable energy, and I agreed with everything you've said up here. My question is, you've done an amazing job at dissecting the cost engineering for the batteries. Have you done a similar dissection of what you referred to as a needed revolution on the policy side, the policy and the market mechanism side? And do you have you kind of evolved the thinking in terms of how do we reinvent the policy and market mechanisms to make this future happen?
Yeah, well, thanks for the kind comments. Not as much on the policy side. It's just not. We're certainly doing some, and we're building relationships with all the different CPUCs and utilities, and and even the sort of state and federal regulatory people around this, but it's not our real big focus. Tesla is an innovation company at the core, and we really focus on creating products that then end up driving a need for change in the regulatory environment. I'd say that's kind of our cycle of chicken and egg on how we want to focus on this. I think it's very hard to create and educate people on the need for new regulations based on hypotheticals. And they're incredibly conservative by nature, and just because they've had to be based on trying to have reliable service for millions of people. So it takes a really strong imperative that's very low risk in both technology and production readiness and ability to ramp and scale to have something compelling to really take up the regulatory change. So that's part of why we've come into this on the back of the automotive industry, where we can say this is very low risk. We have many gigawatt hours of cars zooming all around in different countries, doing duties that are enormously more aggressive than these stationary packs. This is like where an automotive pack goes to take a nap. It's incredibly boring. The peak power rates are C/2 instead of 4C or 5C. Charge rates are similarly benign. So there's the vibration's easy, the thermals are easy. On every level, it's more conservative. And then also on the volume and capacity side, we can clearly demonstrate, to these people that this has the ability to ramp. It's not, there's not an invention needed here somewhere to scale it beyond a laboratory prototype. It's kind of a 1% of our current production mix, and whether we dial it to 2 or 5 or 10, it doesn't really change the risk profile at all. So that's how we're attacking the regulatory side. Maybe I missed your comment on recyclability. I'm sorry. That's a very important point, and I wanted to come back to it. I think it's one thing that people don't fully appreciate, that the batteries don't consume themselves. It's totally different, than an internal combustion engine. When you build the car and ship it, when it comes back into the junkyard, whenever that might be, every element that you built into the car, every atom of nickel and all the other valuable materials are still in there. So we're already starting to look at reprocessing and adding reprocessing and recycling into the Giga Factory as kind of a front-end operation. And there's already some compelling ways where you can take raw battery material and reprocess them if you have enough volume and flow back into battery precursors. You'll probably need to pretty heavily reprocess it because things corrode and they oxidize and morphologies change, but the elements are still there. So that's going to be a huge industry in the future. The challenge is everything's growing so fast right now that if you're growing at 100% per year, the field returns from 10 years ago are not very significant. So anyway, thanks for that. Yeah.
I wanted to ask you about the battery technology itself on 2 levels. One, it seems that the tacit assumption is that it's lithium forever, sort of like crystal silicon in solar. It's just never going to get beat by something else. So do you agree with that? And the second question is, could you comment on the religious and philosophical divide in the world between 18650 structures and things that look like pocketbooks or cereal boxes?
Sure. Well, it definitely is not lithium ion forever. Forever is a long time. But I think it is lithium ion for probably 5, maybe 10 years. And I'm the first person that's hoping and they're rooting for battery innovation improvements in whatever form they come. If it's a high energy density ultracapacitor that can beat the pants off lithium ion, great, that'd be awesome. So much the better, because it'll accelerate cars, it'll accelerate stationary storage, all of it. But we're not waiting, and I think that's another dangerous game that people get into is, when you look at technology that's improving, at any technology, there's always a temptation to just wait and do nothing. But we're seeing an ability to get to price points and economies and business models that just make sense on their own right. So if you're making a positive return, do you care if you waited? I mean, it's you can always do more later. You can grow even faster with better technology later. But doing nothing is a worse business case. So that's why we're comfortable making this big investment. And the other thing is, looking historically as kind of a guide to at least some of the future innovations. A lot of them don't come as like a total upheaval of the whole architecture. There will be a better cathode material, there will be a better electrolyte, better separators. All this is already in the works. And much of that can still reuse the same infrastructure for building cells, building packs. At some point, that's all going to get turned on its head. It's hard to imagine what 50 years looks like. But for the next 5 or 10, I think it's going to look somewhat similar with better and better materials and better chemistry couples going into cells. And I think we can almost double energy densities in that same line of reasoning, with better anode and cathode materials largely. And you'll still have coating machines, you'll still have formation machines, all the same infrastructure around that looks somewhat similar. But if it gets better and if there's a compelling reason to change it, hey, great. It accelerates the core business even faster. And to this philosophical divide on form factor of cells, it makes no sense to me. I think people are totally hung up on the shape and size of the cell, but it's for no good reason. What really matters is what's inside the cell. I haven't talked a lot about an 18650 just because it really doesn't matter. At the volume levels we're working at and the scales, you need to be focused on materials cost and the overall performance parameters of the resulting cell, both safety and thermal. And we've looked at that pretty deeply and done the best optimization we can think of, starting from kind of physics principles, and come to a conclusion that we think today, with today's technology for cells, a relatively smaller form factor is a pretty good optimization for safety and thermal and cost reasons. I don't think that's exactly an 18650. It's probably a little bit bigger than that. I think cylindrical is probably still what makes sense from a cost point of view. So there's a lot of little drivers here, but it shouldn't be some philosophical debate of right or wrong on this or that. Some other applications that have much higher power to energy ratios, will move toward different form factors and different cell construction methods. In the auto industry and the big OEMs, I think, have really fallen in love with big form factors because it seems like it moves the problem, it somehow makes the problem simpler, but it just moves the complexity inside the cell so that they don't have to think about it. There's just as many parts and interconnects inside of a big cell as there are in a collection of small cells. So it's it's not really good reasoning to imagine that somehow that has better reliability if you just have 100 bolted connections in a car instead of a whole bunch of interconnects between small cells that you can see being made at the module and pack level. So anyway, that I could narrate on that for a long time, but it seems to have actually somewhat quieted down. 3 or 4 years ago, this was a really intense debate, and it's kind of dropped away a little bit. Yeah.
I'm Ron Perry. I'm a pleased shareholder of Tesla. One thing you didn't talk about was the deployment plan and the pricing metrics for the stationary battery storage, commercial sized.
Sure. It varies based on different customer base and what type of product it is. So on the residential side, those are being leased to customers through SolarCity. And in a lot of cases, that's being kind of bundled in with the sort of financing that goes with the solar system itself. So that's one model. Then on the commercial, the sort of mid-sized commercial model, it varies a little bit depending on the customer. This is where you see sort of the bleeding edge of this industry. It's not really well sorted out with a single kind of structure yet. But some people would prefer to buy them outright. Many prefer to not own it and to let Tesla maintain ownership. And we basically, we work with SCHIP. We'll work with the utility on interconnection and do everything else, and just provide the host customer savings. So that's somewhat akin to how a lot of solar systems work today that are 100% financed or owned by a third party. At the end of the day, the customer might not want to try and arbitrage their energy every single day. As exciting as that is, and it's kind of fun and cool, but I can try to do that at my house for a while, and I still got busy and bored with it, and you forget about it. You need somebody else to really maintain it and keep it running at high value. So I think in the end, we or a third-party financing company will end up owning a lot of those assets and operating them, for host customers. Now, utility scale might be at another side where you get to much larger scale systems that are more like financing a power plant kind of thing, because you're getting into the tens or hundreds of millions of dollars.
So have you developed an operating center to dispatch and store and dispatch the cells themselves at commercial plants, or you're not to that scale yet?
We are building that right now. So.
Thank you.
Kumar Goginini with ChargePoint. Can you talk a little bit about the failure rate?
Sorry,
And warranty
Oh, there you go. Sorry. The failure rate of which product?
of the whole system, battery pack system, and warranty.
Well, it's quite reliable. I mean, we've sort of beaten that up on the car side pretty thoroughly, and that's given us the sort of familiarity with the experience of harsh environmental conditions and the cycling and thermals. And as I sort of alluded to before, the environment for the stationary pack is really much more easy to deal with from a reliability and abuse point of view than the vehicle. So the downside is we probably over-designed and have too much cost carried in some of those systems, but on the good side, the warranty has been quite good so far. So we don't see really cell failures or module failures. The only issues perhaps we've had have been we've had circuit breakers that were headaches. We've had interconnects and switchgear that's problematic. Those kind of things, but the problems don't trace back to the fundamental cells. That's really very robust. I'm not sure if that gets at your question or not, but.
What about the degradation when you're discharging and charging the batteries as a stationary storage?
Well, the degradation profile is, it's the same chemistry that goes in our cars, so it's very similar to that. And we've optimized for around a 10-year life. And this is also a big philosophical debate, with OEMs on cars and with stationary storage as well. And I think it's a tough optimization from an engineering point of view, because certainly you can pick chemistries that might last 20 or 30,000 cycles. Or you can pick chemistries that might last 200 or 300 cycles. But we're somewhere in between. And I think striking the right balance between not overdoing it on cycle life in some ways, so that the thing is just you're paying too much up front for a product that will be pristine when it's obsolete. That's kind of the simplest way maybe to explain that. You want something that uses itself up in the most productive way and does the most good cycling and storing energy for whatever purpose. And is kind of nearing its end of life, right when we think replacement technology is at a place that's very compelling to remanufacture the cell stack.
I think we only have time for one more question right over here.
JB, great presentation. My name is Ryan Wartina. I'm with one of those little software companies called Jolly, doing control systems. And the question that didn't really come up is, what's your perspectives on the power converter? And where, that's a very expensive piece right now. Where can that go? Are you guys going to build one yourselves? Is it modular?
Yeah, I didn't talk too much about that. Just the nature of the conference, but we are building it ourselves actually, and it's a critical part of this whole thing. Selling someone a battery is not a very compelling value proposition by the definition of what a battery is. You really need an AC energy storage device that is controllable and dispatchable. So power electronics, inverter chargers, cooling systems, all of it. You just want a product that does that. And this is something we learned very firsthand in the propulsion side of cars. Having just a motor or outsourcing different pieces of it was sort of hopeless. And we focused on the system design and all the system integration. And we've kind of taken that same mindset into stationary. We build our own chargers right now for the car. We build our own drive inverters for the motor. So our current production rate of power electronics components, also in Fremont, is way in excess of what we need for this. Every Model S gets either 10 or 20 kilowatts of totally isolated, grid-connected charging, and So anyway, we're leveraging that expertise to marry up with these energy storage systems, and the price there is dropping pretty fast too. You see the same trend in solar inverters, but it'll be sub 10 cents a watt in the not too distant future.
Well, let's take a moment to thank our keynote speaker, JB Straubel.